Okay, so in this video we are going to implement the Dijkstra algorithm itself. So let's get started. I'm going to have a method public void compute path. Of course we have to define the source vertex or the starting vertex, whatever we call it. Okay, and basically we have to set the source vertex. So the source vertex dot set distance to be equal to 0, because the distance is initialized to be 0 for the source vertex or the starting vertex. And I'm going to create a priority queue, and basically it's going to store the vertices, and that's why we have to implement the comparable interface for the vertex, because this priority queue is going to order its content. And okay, it's going to pose the question that according to what we have to order the vertices, and of course according to the distance parameter. Okay, so I'm going to name it priority queue whatever is equal to a new priority queue. Of course, at the beginning we have to add the source vertex with the distance set to be 0. And basically the algorithm itself is that we have to iterate until this priority queue is not empty. Okay, then we have to get the actual vertex. The actual vertex is equal to the priority queue dot pole. And if you hover your mouse on the pole, then it's going to retrieves and removes the head of the queue. What does it mean? Or okay, it's going to return null if the queue is empty. But what's important is it's going to remove the head of the queue, and the head of the queue is going to be the vertex that has the minimal distance. Why? That's why we have implemented this comparable, that we would like to order the vertices in the priority queue according to the distance parameter. And it's going to order the distance parameter according to the distance. Okay, so we have the actual vertex, the vertex with the minimal distance from the starting vertex. Then we have to consider all of its neighbors, so the edge in the actual vertex dot get adjacent list. And basically we have to get the v. So the v is going to be equal to the edge dot get the target vertex, and basically that's why we don't need the start vertex, because the start vertex is the actual vertex. Whatever it means that we consider all the neighbors of the actual vertex, so we iterate through the actual vertex adjacencies list, which is going to return the edges, and the edges is going to point to the neighbors, so we just have to get the target vertex. The start vertex is going to be the actual vertex, so we don't have to get it. Okay, and we have to define a new distance, so a double new distance is equal to the actual vertex dot get distance from the starting vertex, plus we have to consider the edge dot get weight, because that's what we have been discussing in the theoretical section, that this actual vertex get distance is going to define that what's the cost to get from the starting vertex to the given vertex, to the actual vertex. And of course there's another cost, the edge.get weight, that we have to consider when we would like to visit the neighbors, of course. And basically if this new distance is a better solution, what does it mean? That the new distance is smaller, so there's a shorter path. So if the new distance is smaller than the v.get distance, then of course we have to update the priority queue, because we found a better solution, a shorter path. So first of all I'm going to have the priority queue.remove, and we have to remove the vertex v. Then we have to update, so set the distance to be equal to the new distance. We have to set the predecessor, because that's how we are able to track the shortest path itself. So we have to set the v.set predecessor to the actual vertex, and of course we have to add it back to the queue. So the v add to the priority queue. Okay, and basically that's all about the algorithm itself. Then of course we will have another method, the public void, or sorry, it's not going to be a void, it's going to return a list of vertices. So vertex get shortest path to, and of course we have to define the target vertex for which we would like to define the shortest path. Of course we have to import the java.util.list. I'm going to have a list of vertices, the shortest path to target, for example, is going to contain the vertices we have to visit for the target vertex. Okay, it's going to be a new array list. And basically we backtrack. We start at the target vertex. So vertex is equal to a target vertex. And basically, while the vertex is not equal to null, we just have to set the vertex to be equal to the vertex.get predecessor. So that's why we have to set the predecessors, because that's how we are able to track the shortest path itself. Okay. And basically, as far as we bump into a null, we are going to backtrack. So we get the predecessors and we start at the target vertex. And of course, we just have to add these vertices to the shortest path. So the vertices are being added to the shortest path. Here I'm going to reverse it because it's going to have in a reverse order. So I'm going to reverse the shortest path to target, and I'm going to return the shortest path to target. Okay, so basically that's all about the algorithm where we find the shortest path to every other vertex starting from the source vertex. And we have the get shortest path when we are going to backtrack with the help of the predecessors and we are able to build the shortest path. We have to reverse it with the help of the collections and return it. So in the application, I'm going to have just a demonstration application. So I'm going to create a vertex 0 is equal to a new vertex A, for example. I'm going to have just 3 vertices, the vertex B and the vertex C. Okay, and for example, I'm going to have the vertex 0.addNeighbor, a new edge with weight 1. And the starting vertex will be the vertex 0 and the target vertex will be the vertex 1. So we will have an edge pointing from the A to the vertex B and the edge weight will be 1. Then if, for example, I add another neighbor for the vertex 1, for the vertex 0, the edge weight will be 1 again, from the vertex 0 to the vertex 2, and I'm going to add an edge from the vertex 1 to the vertex 2 with the edge weight 1 again, and I'm going to add it to the vertex 1. So what does it mean? It means that if we would like to get from A to C, then of course we can go directly. There's no point in going from A to B and B to C because the cost would be 2. And if I go directly from A to C, then the cost would be 1, so it is the shortest path. So I'm going to instantiate the Dijkstra's algorithm. Okay, I'm going to have the algorithm that compute path. The source will be the 0, so it's going to compute every shortest path from the starting vertex, which is the vertex 0, the vertex A basically. And I'm just going to print out the algorithm that get shortest path to the vertex 2. So I would like to get from the vertex A to vertex C when edge weights are all 1. Of course, what will be the solution? I'm going to run it. Okay, we can go directly from A to C. But what if the edge weight is very, very big when I would like to go directly from A to C? So there's an, sorry, not that. I'm going to change this. So the edge weight is, for example, 2. I don't have to define a huge number because whenever the neighbor, sorry, let me come, okay, it's going to be okay. So in this situation, when the edge weight between the A and the C is bigger than the, okay, it's not bigger, I'm going to write 3 because 1 plus 1 is equal to 2, so okay, that's the threshold. But anyways, in this situation, it would be better to go from A to B and then B to C instead of going directly from A to C. So basically, our shortest path algorithm is working fine. You can check it on greater graphs, whatever you prefer. And basically, that's the core of the algorithm. We have to create a priority queue, and that's why vertex class has to implement the compare to interface. And basically, while the queue is not empty, we have to look for better solutions. So shortest path, whenever the new distance is smaller than the v.get distance, we have to update the priority queue because we have managed to find a shorter path. And we have to iterate it as far as the priority queue is not empty. Thanks for watching.